Okay. Today, Archita,
Yes, sir.
today we will start new chapter. Name of the chapter is moving charges. Okay, moving charges, moving charges in magnetic field. Following moving charges in
Magnetic field.
is it moving
Yes.
charges in magnetic field? Okay,
Yes, sir.
yes. Ah. You see, magnetic field అంటే a current carrying conductor produces magnetic field. A current carrying conductor, a current carrying conductor, current carrying conductor produces what?
Magnetic field.
Magnetic field. Produces magnetic field. Okay?
Yes.
Current can cause heating effect also. Due to current, there is a heating effect. And whenever current is passing through a conductor, heat is produced in the conductor. Also, whenever current is passing through a conductor, magnetic field is created around the conductor. Is it?
Yes, sir.
And also, around a magnet there is a magnetic field. For example, around a magnet, around a magnet there is a magnetic field. There is magnetic field. Magnetic field. For example, suppose there is a magnet. Suppose I am showing bar magnet. Bar magnet has north pole and south pole. North pole and south pole. You know, magnet has two poles.
Yes, sir.
Magnet has north pole and south pole. Around a magnet there is a magnetic field. And in class 10th, you have studied something about the magnetic field around a bar magnet. And that
Yes.
magnetic field we can represent by drawing lines. And these lines you have to draw from north to south. And the magnetic lines are from north to south. And inside the magnet they go from south to north. Inside the magnet, magnetic lines from south to north. So this is one magnetic line. And similarly, you can draw one more line this side. This is a magnetic line, magnetic field line. What is what is the direction of magnetic field? Magnetic field lines are outside the magnet. They go from north to south, and inside the magnet they go from south to north. Is it?
Yes, sir.
Inside the magnet they go from south to north. Please wait. So is a magnet. This is a magnet, and inside the magnet, this line go from south to north. Like followed, I think.
Yes, sir.
Okay, and also this magnetic field is denoted by letter B. Magnetic field denoted by letter B. Right. Yes. This is a magnet. The north pole. The other is this pole. Okay. One side is the north pole, and the other side is the south pole of magnet. And magnetic lines inside they go from south to north, and outside they go from north to south. These are magnetic lines. And magnetic field is represented by letter B. Magnetic field represented by letter B, and it is a vector quantity. The way electric field is represented, denoted by letter capital E, E bar.
Yes,
and
sir.
magnetic field denoted by letter B bar. And around the magnet, if we keep another magnet, around a magnet, if we keep on a small magnetic needle, the magnetic needle will deflect. Why the magnetic needle deflect? Because of the force given by the magnetic field of this bar magnet. So this is bar magnet. This is a bar magnet. Bar magnet. Okay. So the point is that around a current carrying conductor there is a magnetic field. Around a magnet also there is a magnetic field. Okay. Now
Yes,
this
sir.
magnetic field denoted by letter B, and unit of magnetic field is unit of magnetic field is Tesla. What is the unit of magnetic field?
Tesla.
Tesla. And in short form we write capital T, Tesla. Tesla also can be written as it also can be written as Newton per ampere meter. Tesla also can be written as Newton per ampere meter. Newton per ampere meter. Also Newton by ampere meter. So please remember unit of magnetic field is a Tesla, and it is a vector quantity. It is a vector quantity, and the direction of magnetic field at a given point is along the tangent drawn at the point on the magnetic line of force. And suppose there is a current carrying conductor. Current carrying conductor. For example, this is one plane surface. Plane surface is a plane surface, and one straight conductor. Consider one straight conductor. Straight conductor. This is a straight conductor. Current through this conductor is a I amperes. Now, as current is passing through this conductor, now around the conductor there is a magnetic field lines. There is a magnetic field. That magnetic field we represent by drawing lines, sir. Now here the magnetic lines are concentric circles like this. Around this you have to draw lines. This is one magnetic line. This is another magnetic line of force. Magnetic line of force. Okay. These are this is the plane surface. Now these are magnetic lines. Magnetic lines around what? Around a magnetic lines
Uh,
around what? Around a straight current carrying
Conductor.
conductor. And what is the direction of current? Direction of current is upward or downward here?
Upwards.
Upward. If direction of current is upward, then magnetic lines around the conductor is concentric circles with anti-clockwise direction. Concentric circles with anti-clockwise direction. Like if current is downward, if current flowing through conductor is downward, for example, like this is one surface. This is a surface, and imagine one straight current carrying conductor. Straight current carrying conductor. Wait, this is one plane surface, and you consider a straight current carrying conductor. This is the conductor. Now current is going down. Sorry, I want to show current is in downward direction. This is a straight conductor. Okay, straight current carrying conductor. Yes. Now what is the direction of current? Current is going in which direction?
Clockwise.
No, no. Current direction of current is
Oh, sorry, sir. Downwards.
downward, sir. If direction of current is downward, then around the conductor the magnetic field lines are concentric circles with a clockwise direction. Magnetic lines around this conductor is concentric circles, concentric circles with a clockwise direction. Like this. These are magnetic lines. Okay. So how to decide? How to decide direction of magnetic lines? Sir? Direction of magnetic field lines can be decided by right hand thumb rule. Right hand thumb rule. Right
Sir,
hand.
one more rule is also there, right, sir?
Huh?
One more rule is also there, right?
One more rule is this one. One more rule means actually what is that one more rule? What do you say?
So we have to rotate our palm in the
Yes, yes.
thumb
You
should be pointing towards the
yeah.
current.
Thumb should be pointing in the direction of current, and then you rotate your palm fingers. Okay. Thumb is in the direction of current. Then rotate the fingers like this. Thumb should be in the direction of current. Thumb, right hand thumb rule. Right hand thumb rule. Thumb rule is used. Right hand thumb rule is used to find what? To find the direction of magnetic
Magnetic
field.
field.
To find the direction of to find the direction of magnetic field. To find the direction of magnetic field around
Current,
a
current carrying
yes,
conductor.
around a current carrying conductor. Around around a current carrying conductor. Around a current carrying conductor. Around a current carrying conductor. Right hand thumb rule. All right. What is the right hand thumb rule? And if you have to keep thumb in the direction of current. Thumb should be in the direction of current. Thumb should be in the direction of current. Thumb in the direction of current. Right hand. Right hand thumb. Right hand thumb in the direction of current. In the direction of current. Then the fingers. The fingers will show. Understood? Right hand thumb in the direction of current, and then the fingers, then the palm fingers, then the palm fingers. Uh, Fold the fingers. The direction in which the fingers are folded, that is the direction in which magnetic lines. I hope you are following. I think.
Yes, sir.
Hello.
Yes, sir.
Okay. Thumb is in the direction of current. You have to keep. Then thumb in the direction of current. Then then the direction in which then the direction in which palm fingers are folded, in which palm fingers are folded. Okay.
Yes, sir.
Palm fingers folded gives the direction of
Magnetic field.
gives the direction of magnetic lines, gives the direction of magnetic lines. All right.
Yes, sir.
uh, Now, for example, suppose a thumb I try to draw. Okay, I try to draw like this. Hmm. Suppose a thumb direction. Okay, thumb direction. Then the fingers. These are the fingers in which, yes, like this. Yes. and the direction. Suppose this is the conductor, current is going like this. This is the direction of current I. Is it? Direction of current is I. Now you fold the fingers. If you fold the fingers like this, if you fold this way, the direction of magnetic lines around it. Alright?
Yes, sir.
Okay. Right hand thumb. Now. So the point is now finally around a current carrying conductor there is a magnetic field. Around a bar magnet there is a magnetic field. Okay. Why there is a ante to get magnetic field, to create magnetic field there should be a current. There should be a current. Even in a bar magnet also there is a current. In the bar magnet actually there are atoms of that material. In the atoms electrons revolve around the nucleus. The electrons which revolve around the nucleus they create magnetic field. So even in the bar magnet also there is a current. Current means that is due to revolution of electrons around the nucleus. That revolution of electrons create magnetic field. Okay.
Yes,
Now
sir.
magnetic field denoted by letter B and its unit is a Tesla. Also you can write it as a Newton by ampere meter. Now we are coming to one important point. What is the force on a charged particle moving through magnetic field? This is important point. Force on a charged particle, force on a charged particle, force on a charged particle moving through magnetic field, moving through magnetic field, moving through magnetic field. Alright, force on a charged particle moving through magnetic field. Important. This relation is important for CBSE examinations. Suppose a charged particle moving through magnetic field. When a charged particle moving through magnetic field, the particle experiences force. So force on the charged particle, the formula is F bar is equal to Q into V bar cross V bar. Q into V bar cross V bar. This if you write only magnitude of force, if you write only magnitude of force, F bar, only magnitude, you can write like this, F is equal to QVB sin theta. QVB sin theta. In this equation, you should know the meaning of each terminology, each and every term. In this F is force. F is the force. Force means force on the charged particle. Q, charge of the particle. V, velocity of the particle. Here Q, charge of the particle. Q, charge of the particle. For example, if the electron is moving through magnetic field, if electron is moving through magnetic field, then the charge on the electron you have to take 1.6 into 10 power minus 19 coulomb, like that. So Q, charge of the particle. V, velocity of the particle. V, velocity of the particle. V, velocity of the particle. Okay, and B, magnetic field. Theta. What is the theta here? Theta is the angle between. Theta is angle between the direction of V bar and V bar. Theta is the angle between. Theta is the angle between direction of velocity and direction of magnetic field. Angle between V bar and B bar. So very important relation. Force on a charged particle in the magnetic field F is equal to QVB sin theta. So the force depends upon charge of the particle, depends on velocity of the particle, also depends on strength of magnetic field, and it depends on angle theta. So force depends on four factors. F is equal to QVB sin theta. QVB sin theta. So F depends on four factors. F depends on four factors. Four factors. What are the four factors? Q, V, B, and theta. F depends on 4 factors. And here, when the force is maximum, when does the force is maximum? F is maximum when theta is 90 degrees. F is maximum. F is maximum. You get one more questions in CBS examination. When does a charged particle experiences maximum force in the magnetic field? When does means when velocity of the particle is perpendicular to magnetic field. F is maximum when theta is 90 degrees. What is theta? Theta is angle between V bar and V bar.
Yes.
And what is that maximum force? What is that maximum force? Chepu, tell me what is that maximum force?
QVB.
QVB, because sin 90 is 1. As sin 90 degrees 1, F maximum is QVB. Sin 90 is 1. Sin 90 degrees is 1. Therefore, maximum force on the particle, charged particle in the magnetic field is QVB. Alright?
Yes, sir.
Okay. And also, one more important point here. If theta is 0 degrees or 180 degrees, theta 0 degrees or 180 degrees, theta 0 degrees or 180 degrees, then the force becomes 0. And a charged particle do not experience any force when the charged particle is moving parallel to magnetic field. For example, the magnetic field, for example, this is the direction of magnetic field B bar, and the charged particle is moving parallel to B bar. If a charged particle Q is moving parallel to B bar, it is moving parallel to B bar, and here theta is 0 degrees. In this case, theta is equal to 0 degrees. If charged particle is moving anti-parallel direction to B bar, suppose this is B bar direction, magnetic field, and charged particle is moving opposite to the magnetic field like this. This is the direction of V. And here theta is 180 degrees. Here theta is 180 degrees. Sin 0, 0. Sin 180 degrees also 0. So in both cases, F is equal to force experienced by charged particle is equal to 0. So please remember this point. If theta is either 0 degrees or 180 degrees, in both cases, charged particle do not experience any force. And
Yes,
what
sir.
maximum force is F is equal to QVB. And how to decide direction of force? Direction of force is decided by Fleming's left hand rule, or you can decide it by cross product rule. So direction of force, F bar is equal to Q into V bar cross V bar. Q into V bar cross V bar. Okay? If direction of force can be decided by direction of force can be decided by using cross product rule, by using cross product rule, or right hand thumb rule. Cross product rule, right hand screw rule. Cross product rule, right hand screw rule, right hand screw rule. What is this right hand screw rule? Right hand screw rule means if you rotate a screw, if you rotate the screw from V to B, and so you see, yeah, as per this equation, F bar is equal to Q into V bar cross B bar. Direction of force is perpendicular to the plane containing V bar and B bar. Direction of force is perpendicular to the plane containing V bar and B bar. And it can be decided, direction of F bar can be decided by using cross product rule and a right hand screw rule. Or you can use Fleming's left hand rule. Or Fleming's left hand rule. We can decide we can decide direction of force by using Fleming's left hand rule. Fleming's left hand rule. For example, you see, if in a plane, for example, imagine like a surface of a table. This is the surface of a table like this, and one plane surface. This is the surface of a table. In this, suppose V bar is along this side, and this is the direction of V bar. Charged particle moving along this direction, and V bar is along this side. V bar is along this side, and theta is angle between V bar and V bar. Then, if you rotate the screw from V to B, if you rotate the screw from V to B, V to B, if you rotate screw from V to B, then screw will move upward direction. Then the screw will move in upward direction. This is the direction of force. This is the direction of force. Is it? And if you rotate the screw in anti-clockwise direction, if you rotate screw in anti-clockwise direction, then screw will go upward. So V bar cross V bar direction is upward, and the force acts in a perpendicular to the plane containing V and B.
Yes, sir.
Alright. Suppose in the same, if you reverse the direction still, if you reverse the direction of, for example, like this is the surface, this is the surface, this is the surface. Okay. On the surface, V bar is in one direction. For example, V bar is along this direction. Suppose V bar is along this side. V bar, charged particle moving along this side. And V bar is along this side. Then angle between them is, you say, theta. This is theta. Now rotate the screw from V to B. If we rotate the screw from V to B, then the screw will move downward direction. So this is the direction of V bar cross V bar, and this is the direction of force. So please remember, direction of force on a charged particle is perpendicular to the plane containing V and B, and the direction of F can be decided by right hand screw rule. Also you can decide by Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. What is Fleming's
Left hand.
left hand rule? అంటే left hand's thumb. Left hand's thumb is, you have to keep, the thumb will give the direction of force. Left hand's thumb, forefinger and middle finger, you have to keep middle finger in the direction of velocity of the positive charge. Middle finger, and forefinger is in the direction of magnetic field. Forefinger. Forefinger means index finger. Forefinger. Index finger. Index finger is in the direction of magnetic field. Is in the direction of V bar. Index finger is along the direction of magnetic field. And middle finger of left hand. Middle finger is, you have to keep in the direction of V bar. Middle finger is along the direction of along V bar. Along V bar and along the direction of velocity of positive charge. Okay, middle finger is along V bar, and
Yes, sir.
then thumb will show. Then the direction of thumb shows the direction of force. Thumb shows the direction of force. So you have to stretch left hand's middle finger, forefinger, and thumb. You have to stretch them mutually perpendicular to each other. And also you have to keep middle finger in the direction of velocity. Direction of velocity means the direction of velocity of positive charge. And if it is a negative charge is moving, then you have to keep middle finger opposite to direction of velocity of negative charge. and in the direction of magnetic field you have to keep forefinger, then thumb will give the direction of force on the charged particle. Understood?
Yes, sir.
Okay. And you can remember this like father mother child, father mother child, like this you can remember by this way: father mother child, father mother child. Father means force, father means force. Mother means magnetic field, mother is magnetic field. Magnetic field. Child is a current. Current means the direction of velocity of positive charge. Current. Current means means along V bar. Along V bar. Velocity of positive charge. And the thumb is father. Thumb is father. Middle finger, forefinger is mother, child, current. Middle finger is in the direction of current, child. Okay, so and also otherwise you can decide like this also. Suppose in terms of IJK, in terms of IJK, in terms of I cap, J cap, and K cap. I means I cap means along X axis, sir. J cap means along Y axis, sir. K cap means along Z axis. I hope you know this notation.
Yes, sir.
I cap, J cap, K cap. I cap, J cap, and K cap. In terms of I cap, J cap, and K cap. For example, if it is given like this, for example, B bar is along I cap, B bar is along I cap, B bar is ante along X axis, okay, and velocity, velocity is along, velocity along you say J cap, then then force will be along I bar, then F bar will be, then F bar will be along V bar cross B bar. V bar cross B bar means J cross I, along J cross I, along J cross I. J cross I means minus K. And for example, this is X axis, and this is Y axis, and this side is Z axis, X, Y, Z. For example, here B bar is along I cap, B bar is along I cap, B bar. And V bar is along J cap. V bar ante charged particle is moving along Y axis. Then force will be along J cross I. J cross I. Why? Because F is equal to F bar is equal to Q into V bar cross B bar. V bar. V bar is along J. V bar is along J. V bar cross B bar. B bar is along I. So J cross I means along minus K. And if you rotate the screw from J to I, if you rotate the screw from J to I, the screw will go in the negative Z axis. So J cross I, that is equal to J cross I is minus K, and along negative Z axis. And the force will be opposite to this direction, like this. Force will be along this side. You know how to decide in terms of IJK? For example, you can decide by using this one. For example, this is I cap, J cap, and in a triangle, imagine like this, in a triangle, take a triangle like this, I cap, J cap, and K cap. Now I cross J. I cross J is K. J cross K is I. K cross I is J. Tell me, tell me what the how do you find out I cross J means? I cross J is along which side?
I cross J is K, sir.
K along K and along Z axis. J
Yes, sir.
cross K
Along its axis, sir.
along X axis. K cross I,
Along Y axis.
yes. So if you come in ulta direction, for example, if it is the magnetic field is along some direction, for example, uh, I cross K. I cross K, tell me. I cross K is which side?
Minus Y direction.
Yes, minus Y axis. J cross I,
Minus K.
minus K into negative Z axis. Is
Yes, sir.
it?
Yes.
Is it okay?
Yes, sir.
So important, you get one more question, sir, regarding the direction of force on a charged particle moving through magnetic field. Is it?
Yes,
No,
sir.
no, no. I give one question based on this concept. All right. We do a small conceptual question based on this. For example, one example.
Sir, can you go to the starting slide? I want to copy everything.
Wait, wait. Let me explain this also. You will copy next. Okay.
Okay, sir.
For example, one example is an electron. An electron. Electron is positive or negative charge?
Negative, sir.
Negative charge. An electron is moving. For example, electron is moving along. Electron is moving along west. Electron is moving along west, and the magnetic field is and B bar means magnetic field, and magnetic field B bar is along along north. B bar is along north. Then what is the direction of force on electron? What is the direction of force on electron? What is the direction of what is the direction of force on electron? Electron is a charged particle. Electron is moving in the magnetic field here. Then electron experience a force. Then what is the direction of force on electron? Is it? Uh,
Yes, sir.
how to decide is say. First, north, south, east, west. For example, I show like this. For example, this is one plane surface, horizontal surface like a table surface. This is the surface of a table. And north, south, east, west, how to represent it? This side is north, this side is south. Then you tell me what is the right side now? Your front side is north, your
Yes,
back
sir.
side is south. Your front side is north. Suppose you are standing.
Sir,
You,
right side is east.
yes, right side is east, left side is west. Is it?
Yes, sir.
North, south, east, west. Now here what they said, electron is moving along. Electron is
West.
moving along
West.
west. Electron is moving along west. Electron is moving along west means negative charge is going along west means what is the velocity you have to take? Direct
Towards
opposite.
east.
Don't forget this point. Okay.
Yes, sir.
Electron ante negative charged particle. Electron is going towards west. That means you have to take velocity towards east. So velocity is towards east. Velocity is towards east. I hope you
But
are
why
following.
like that, sir?
I hope, huh?
Why like that, sir?
Because the direction of force depends upon charge also, positive or negative. If it in the formula F is equal to Q into V bar cross V bar, there we are taking Q as positive charge. If Q is a negative, then direction of force also will be reversed. So velocity you have to take along
East.
east. Magnetic field is along
West.
No, in the problem
Oh,
what is
sorry, sir.
given?
North.
Along
North.
north. Am I correct?
Yes, sir.
Magnetic field is along north. Magnetic field is along north. Yes, this side. This side is magnetic field. Now you apply either Fleming's left hand rule or right hand screw rule. You can decide. Now you rotate. You take Fleming's left hand rule. Apply Fleming's left hand rule. Fleming's left hand rule. Fleming's left hand rule. As per Fleming's left hand rule, now you have to keep middle finger in which direction?
Sir, towards west.
Uh,
West. Oh, sorry, sir. East, east.
East. As per this rule. Ante kada? I hope you are
Yes,
following.
yes, sir.
Middle finger of your left hand. Middle finger of your left hand. In the direction of
East.
along east. Am I correct?
Yes, sir.
V bar along V bar. Middle finger along V bar. And index finger, forefinger. Forefinger is along.
Sir, middle finger should be along magnetic field, right, sir?
No, no, no. Middle
Oh,
finger is,
yes, sir. Yes, sir. Yes, sir. Yes, sir.
you see this
Sorry.
slide. You see this. Yes.
Yes, sir. Yes, sir. I forgot. I
Forefinger along the direction of V bar. Middle finger along V bar. So here, as per this, uh, middle finger is along east. Am I correct?
Yes, sir.
Forefinger is along
North.
north. Now you put your left hand. Left hand's middle finger along east. Forefinger along north. Then thumb is coming which side? Let me know.
Upwards, sir.
Upward. Very good. So now the force on electron is upward. Now the force on electron is in upward direction. Am I correct? Force
Yes, sir.
will be in upward direction. Yes. Is it okay? Can
Yes,
you
yes, sir.
force in upward direction?
Sir, once can you go to the first slide?
Yeah. Yes. Today we started here. Moving charges in magnetic field. Magnetic field is created by a current carrying conductor. Around a current carrying conductor there is a magnetic field. Similarly, around a bar magnet, around a magnet there is a magnetic field. Magnetic field represented by letter B, B bar, and its unit is a Tesla. Also, you can write it as Newton by ampere meter. Hello. Now, magnetic field represented by on diagram. And suppose if you put into marks, what they indicate into marks? Into marks indicates that magnetic field is
Inside.
inside, into the plane of paper. Understood? This represents B bar, into the plane of paper, into the plane of board, into the plane of screen. If you write on a paper in the notebook, you have to write into the plane of paper.
Yes, sir.
Now, if you put dots, dots indicates magnetic field out of plane of paper. So if I put dots, dots indicates magnetic field out of the plane of paper. Following?
Yes, sir.
Yes, this dots indicates magnetic field out of plane of paper, out of not into, out of plane of screen. Okay,
Yes, sir.
so dots indicates magnetic field out of plane of screen. Into marks if you put on a paper, that means magnetic field into the plane of paper. Okay,
Yes, sir.
now you see when a charged particle enters in the magnetic field, Important this one. When a charged particle enters at 90 degrees to magnetic field. So when a charged particle when a charged particle enters enters into B bar. B bar means, what do you mean by B bar?
Magnetic field.
Yeah. When a charged particle enters into magnetic field such that V bar, velocity of the particle is V bar is perpendicular to V bar. V bar is V bar is
Perpendicular.
perpendicular to
Magnetic field.
magnetic field. Then the particle will follow circular path in the magnetic. Then the particle follow then the particle follows circular path in the magnetic field. Particle follow
Circular path.
in the magnetic field. I show in a diagram. For example, there is a magnetic field here. For example, I am representing with into marks. Magnetic field into marks. Following
Yes, sir.
into mark. This is a magnetic field. Now one charged particle enter in the magnetic field. For example, charged particle, for example, Q. This is a charged particle. Now its velocity is the right side, for example, V bar. Now tell me, what is the direction of magnetic field? What is the direction of V bar?
Sir, can you repeat?
You see in the diagram, I have shown into marks. What into marks indicates?
That the magnetic field is into the plane of.
Into the plane of the board. Okay.
Yes, sir.
Now, what about velocity of the particle in the diagram? Towards right or
Right,
left?
right, sir.
Right side. Now you apply Fleming's left hand rule. In the Fleming's left hand rule, in which direction you have to keep forefinger? Fleming's left hand rule. You have to keep forefinger in which direction?
Um, in magnetic field.
Until you keep forefinger into the screen. Middle finger is in the direction.
V bar, sir.
Now then thumb is coming which direction? Let me know. Then thumb is coming in which direction?
Upwards.
Huh?
Upwards, sir.
Upward direction. So the direction of force on this particle is upward direction. So this is the direction of force. Following I think, what is the direction of force? Upward. So what is the direction of this force at what angle to velocity?
So perpendicular.
90 degrees, perpendicular. So this force, as the force is at 90 degrees to velocity, now this particle will change its direction of velocity. And that force behaves like a centripetal force. And now the charged particle will follow circular path like this. Will follow circular path in the magnetic field like this. Following I think,
Yes,
charged
sir.
particle will follow circular path in the magnetic field. Now you see, if charged particle enters at this place and here velocity is along this side, this is V bar and force will be towards the center. Force is, if you apply Fleming's left hand rule, you get thumb into the this one. Yep. When charged particle enters here, for example, here Q and its velocity is along this side V bar, then thumb will be towards down. So magnetic force will be towards this side. So everywhere in the circular path, magnetic force is towards the center. Force is towards the center. When charged particle is here, velocity is along this side, V bar, and thumb will come toward the center this side. You understood the point, I think? Hello?
Yes, sir.
What the point here? When a charged particle enters in,
Uh,
enters
a magnetic field such that V is perpendicular to magnetic field.
then
Then the
particle
particle
follow which path?
circular path.
Circular path. Very important. Circular path. Now, what is the radius of the circular path? Important. Okay. They ask you derivations. What is the radius of the circular path? What is the
Yes.
time period of the charged particle? Time period means the time taken by the particle to revolve to make one revolution in the magnetic field. Alright.
Yes, sir.
Now the next one is what is the radius of the circular path? Radius of circular path. Radius of circular path. Circular path followed by whom? Circular path followed by whom?
By the charged particle.
By charged particle. Radius of the circular path followed by charged particle. Now we derive expression for this radius. Radius of the circular path. Now you see when charged particle enters in the magnetic field, what is the force on the particle? Force on the particle due to magnetic field. Force on the particle due to what? Force on the particle due to
Magnetic
force on the particle due to magnetic field is what is the force formula Jepu? F is equal to
QVB sin
QVB
theta.
sin theta and theta 90 degrees. If theta is 90 degrees, then it follows circular path. Theta 90 degrees. Then F is equal to Jepu, what is F is equal to Q B sin 90 how much?
1 sin
1. So what is the force on the particle?
QVB.
Now this force acts like a centripetal force. Why centripetal force? Because this force acts toward the center. This force acts as the centripetal force. Acts as centripetal force. This force acts as a centripetal force. What is the centripetal force formula? mv square by r. What is the formula for centripetal force?
MV squared by R.
mv square by r. So therefore we'll equate it. Therefore qvb is equal to mv square by r. Therefore qvb, force on the charged particle due to magnetic field qvb. This is the centripetal force mv square by r. Followed?
Yes, sir.
From this, what do you get? 1b get cancelled on both sides. If 1b get cancelled, you will get qb is equal to
M by R. MV by R.
mv by r. Therefore, r is equal to
MV by Q.
mv by qb. This is the formula for radius of circular path followed by charged particle. R is equal to mv by qb. Important relation. They ask in CBS examination, derive or they say obtain expression for radius of circular path followed by charged particle in magnetic field. R equal to mv by qb. Okay, and you get
Yes,
problems on this equation also. Will you?
yes, sir.
I hope you are following. I hope you are following. This is a circular path, and here is a magnetic field. Same diagram I'm drawing again. This is the magnetic field. Magnetic field. Magnetic field. And a charged particle enters in. Suppose this is a charged particle Q. This force is towards the center, and velocity is along this side v bar. When charged particle is here q, velocity is along the tangent like this v bar, and force is towards the center. Everywhere force acts towards the center. When charged particle is here, how do you know towards the center? You apply Fleming's left hand rule and you can check. This is v bar. Then this is the direction of force F. This Is it okay?
Yes, sir.
When charged particle is here, this is the direction of velocity and force will be towards the center line. Alright.
Yes, sir.
What is the formula for radius of circular path?
R is equal to mv by
mv
qb.
by
qb.
qb. You get numerical problems on this equation mv by qb. What is mv? Mass into velocity. What it is?
Uh, Acceleration.
Mass into velocity is momentum.
Uh, yes, sir.
Mass into velocity. Momentum of the particle divided by qb. Now we did radius. Sir. Now this particle takes some time to complete one revolution. That is called time period of the particle. So next we take what is the time period of the particle. Time period means the time taken to complete one circular path. Time period of the particle in the magnetic field. Time period of the particle. Time period we denote it by letter capital T. How do you get time period? Time period ante time taken for one revolution. Time taken for one revolution. What is the distance for one revolution? Distance traveled for one revolution. How much? Distance for one revolution. How much? 2 pi r. What is the distance traveled for one revolution?
2 pi r.
2 pi r perimeter. Okay.
Yes, sir.
And what is the speed of the particle? With what speed particle is moving? Speed is v. Therefore time taken is equal to distance by speed. Time is equal to distance by speed. Time equal to distance by speed of the particle. Distance how much? What is the distance?
2 pi r.
2 pi r. By speed is
V.
v. 2 pi r by v. Just now we derived what is r? But r is equal to
mv
just now we did
by
r is equal to
mv by qb.
mv by qb. Now put in place of our mv by qb, then you will get therefore time period t is equal to 2 pi r. R place में what do you write in r place?
mv by qb.
mv by qb. 2 pi r by v whole by v. This is the time period. Now this we can write it as 2 pi mv by qb into v. Am I correct?
Yes, sir.
V get cancelled out and what do you get here? Time period. Therefore, what is the time period of the particle?
2
2,
pi m by qb.
2 pi m by qb. This is the formula for time period of the charged particle. Time period of the charged particle 2 pi m by qb. And if you want frequency of revolution of particle, frequency of revolution, how do you get frequency? Frequency is nothing but reciprocal of time period. Hello.
Yes, sir.
Frequency of the particle, frequency of revolution of the particle, frequency nu. We are denoting letter by nu. Frequency means reciprocal of time period. If you do reciprocal of time period, you will get 1 by t. How much you got? 2 by m by
qb.
qb. And this you can write it as qb by 2m. Therefore, frequency means the number of times it revolves per second. Nu is equal to qb by 2 pi m. Following?
Yes, sir.
Here if you observe that equations, time period does not depend upon speed of particle. Time period does not depend upon speed of particle. Note important point here. And when a charged particle enter in the magnetic field, particle follows circular path and the time taken for one revolution does not depend upon speed of particle. If you project the particle with a different speeds, whatever may be the speed it is projected into the magnetic field, it takes same time to complete the path. So
Yes.
note, what is the note? Time period does not depend on, time period does not depend on, time period does not depend on
Speed of the particle.
Yeah, does not depend on speed of the particle. And also radius, we got radius r is equal to mv by qb. R is equal to mv by qb, and radius depends on v. From here, radius is directly proportional to v. More the speed, more the radius of the particle.
Yes, sir.